Hi everyone. So in this video I want to talk about the lidocaine GC experiment that you're going to be doing in the lab. So lidocaine, although it's not really a drug of abuse in humans, it's used as a numbing agent in people. It is a drug of abuse in horse racing. So for example, if a horse has an injury, some unscrupulous people may inject lidocaine into the horse so that it can't feel that. It's a numbing agent, and therefore the horse can run, and it's a kind of a problem. So the lidocaine, it doesn't have a direct human forensic application really, but it does have a forensic application in horse racing. Furthermore, this process that you're going to do could be done for cocaine instead of lidocaine or a metabolite of cocaine or something like this. So basically, we're looking at an example here. Again, that doesn't have a direct forensic application, but the methodology is the same. So let's look at lidocaine. All right, this molecule here is lidocaine. So we have these two groups here. We have this amide group and we have this amine group. Of course, we have a ring here too. All right, and what we'll notice is, if you remember from your organic chemistry, which maybe you're in right now, amines are organic bases. So this amine is capable of accepting a proton from an acid. And this is lidocaine HCl. And it turns out that in horse racing, if they were going to inject the horse, they wouldn't inject them with this. They would inject them with lidocaine hydrochloride, the salt, for the very simple reason that horses, just like people, are aqueous based, right? We're water based. And this molecule is soluble in water, and this molecule is not. So therefore, lidocaine HCl would be the more likely culprit that you would find. And this has some implications in your liquid-liquid extraction. So now to talk about how we're going to do this liquid-liquid extraction. So there's kind of two parts to this, all right? You're going to have a urine sample which has some lidocaine in it, and you're going to also have to make a calibration curve. You're then going to take your extracted sample, inject it into the GC, get a peak area, use your calibration curve, which again, you're going to have to inject all those samples into the GC and those peak areas to determine the amount of lidocaine in the original urine sample. So how are you going to do that? Well, if you have lidocaine HCl in the urine, you're not going to be able to extract this into an organic solvent. Why not? Because this is an ionic compound. It's not going to have any affinity for dichloromethane here. So instead, you're going to add a base. And when you add this base, the sodium bicarbonate, which is just baking soda solution in water, you're going to deprotonate this and make this molecule without the proton. This molecule is a large organic molecule, certainly soluble in dichloromethane. You're going to have some byproducts here. The carbonic acid H2CO3 breaks down into water and carbon dioxide. And then the Na goes with the Cl to make NaCl. Note that these concentrations are fairly low, so you may not actually see bubbling here. Also note that the concentration of lidocaine is high enough in this sample to be seen by GC that you may actually see a precipitate when you add the sodium bicarbonate. So if you do see this precipitate, then you know you've got the lidocaine out. In real life, chances are the lidocaine wouldn't be that concentrated, hopefully not. So therefore, in that case, you probably wouldn't actually see a precipitate because this would be in such low concentration that you wouldn't be able to see it come out. However, with an FID detector, it wouldn't be sensitive enough to detect it. So we have to crank up the concentration of this a little bit in order to ensure that you have enough to see it. So here's what you're going to do practically for the liquid extraction. You're going to take a 25 milliliter urine sample, which contains some lidocaine HCl, and your job is to determine how much. You're going to add sodium bicarbonate solution until it's basic. Again, you may see a precipitate, but you can certainly take a stirring rod, touch it into the solution, and then touch it to a piece of pH paper and make sure that it's reading basic. If it's reading basic, then you know you've deprotonated the lidocaine. Then you're going to add 25 milliliters of dichloromethane. Note that you have the same volume of the solvent you're using for extraction and the urine sample. So therefore, this just saves you a calculation at the end. You won't have to do an extra calculation because they're the same volume. Then you're going to extract this using a separatory funnel. And when you do this extraction, you need to remember that the dichloromethane layer is at the bottom, for the simple reason that dichloromethane is more dense than water. So these two layers won't mix because they're immiscible solvents, water and dichloromethane will be at the bottom. Note that if you're taking the organic chemistry lab or you took that in the past, usually we use ether, and ether is up at the top. In organic too, we do use dichloromethane sometimes as well. All right, then you're going to dry it with anhydrous sodium sulfate, add 2 milliliters to a GC vial, and inject, and get a peak area for your lidocaine sample. Okay, so that is basically how the extraction is going to work. I didn't mention it before, but I just want to talk about it briefly now. You may be asking yourself, why didn't you just inject the urine in the first place? Well, if you start injecting urine, which has salt and urea and all these other compounds in it, it's going to muck up the detector, the injector, and it's going to cause all kinds of problems with your GC. So we don't want to do that. So instead, what we're going to do is we're going to extract it first. The next thing you need to do is to make a calibration curve. And if you recall from general chemistry, a calibration curve is a series of known samples, and then we're going to look at the detector response. Essentially, what a calibration curve allows us to do is it allows us to take something that's relatively easy to measure, such as the peak area in a GC chromatogram, and relate it to something that's relatively difficult to measure, like how much lidocaine is in a solution. And we do that with a series of known values, and we look at the detector response. So specifically, you're going to take 20 mg per milliliter, 10 milligrams per milliliter, 5 milligrams per milliliter, and 2.5 milligrams per milliliter lidocaine solutions. So you need to make these 4 solutions. You need to be super aware and ready to make these solutions as soon as you come into lab, because there is some time on the GC instrument and you don't want to spend all your lab time making your solutions. So to do this, what you're going to do is you're going to take around 1 gram of lidocaine and put it in a 50 milliliter volumetric flask. You're then going to fill to the calibration line with dichloromethane. This is 1,000 milligrams in 50 milliliters. If you do the math, you find that this is 20 milligrams per milliliter. Then you're going to do some serial dilutions in a 10 milliliter volumetric flask. So if you take 5 of the 20 ml solution with a pipette, and then you fill to the 10 milliliter calibration line, you'll now have 10. It'll be half as concentrated. If you take 5 of the 10 mg per ml solution, into another 10 milliliter volumetric flask, and if again filled to the calibration line, you'll have 5. And if you take 5 of the 5 milligram per milliliter solution into another 10 milliliter volumetric flask and fill to the calibration line, you'll have 2.5. So that's how you're going to make your solutions in order to do the calibration curve. Then you're going to use this GC method here. This GC method is in your lab manual, and we showed you how to set up the GC in the previous video, so I'm not going to talk about that too much. Then finally, you're going to make a calibration curve. You're going to inject all of your standard solutions, your 2.5, your 5, your 10, and your 20, which I have shown here. Note that this is completely made up data, so I don't know exactly what peak areas you will get, so don't expect to get exactly this. Okay, so this is the detector response for these different solutions. A couple things to note. As there is more lidocaine in solution, going from 2.5 to 5 to 10 to 20, there is a greater peak area. We would expect that. Also, there's a linear relationship between these two things. So the R squared is very close to 1, which indicates that the curve fits the data well. If your R squared isn't close to 1 and you have a peak point like down over here or something, you're going to want to consider to remake that point. So do consult your TA, work carefully, and try to get your R squared as 0.99 or better for your calibration curve. So this is a calibration curve which relates measurable data, peak area with GC, to things that are difficult to measure, like lidocaine concentration in a liquid. We would now shoot an unknown. Let's say that our unknown had a peak area of 225. Well, the peak area is a y value. You have an equation of the line, y equals mx plus b. If you solve for x, that will be your lidocaine concentration. So if we use 225 as an example, it's going to be somewhere right around 10 mg per milliliter. I would like you to use the equation of the line. Excuse me, it's going to be a little higher than that. I didn't use 225. So if we use 225 as an example, we go to the line, we go down. It's going to be somewhere around 12 or 13 milligrams per milliliter. But if we use the equation, we'll get a better value there as opposed to just looking at the graph. So if it's been a while since you've made a calibration curve graph, or you didn't take general chemistry general chemistry here, we do this a lot in Gen Chem. I have pasted a link to a video in the description of this video that I use in the Gen Chem lab. It is not lidocaine concentration versus peak area. I think it's density. Density data versus percentage of something in a solution. However, the calibration curve idea is the same, and how to actually make this calibration curve and get the R squared and the equation on Excel is the same. So if you haven't done this in a while, you might want to watch that video. It's a pretty brief video. So to recap very briefly, we are going to determine how much lidocaine HCl is in a urine sample. We are going to do that by extracting the lidocaine HCl by making the solution basic and then dissolving it into an organic solvent, specifically dichloromethane, which is going to be our bottom layer. We're going to inject that and get a peak area. We're going to use that peak area and a calibration curve with 20, 10, 5, and 2.5 milligram per milliliter lidocaine made by serial dilution. We're then going to inject all of these things into our GC. With the knowns, the 2.5, 5, 10, and 20 solution, we're going to use our calibration curve. We're then going to use the peak area of our unknown, and y equals mx plus b, plug in for y, solve for x, and determine the concentration of lidocaine in our original urine sample. So I thank you for watching this video, and I hope you found it helpful, and I hope it gives you some idea of what's going on in the lab this time. Thanks a lot.